Academy of Sciences in the area of quantum information and has been a referee for prestigious journals. Currently, he's professor at IISA Kolkata. So, Prashanta, could you please share your slides? Prashanta, are you there? I can see you logged in. Yeah, okay, great. Great.
Yeah.
You can just share your screen.
Yeah, I'm doing that. I'm doing that. I'm doing that.
Yes, sir. Get to it.
Yeah.
So it's a 30-minute talk, Prashanta, with 10 minutes for questions. So after 30 minutes, I'll just kind of interrupt you.
Sure. थोड़ा वेट तो उसके बाद क्या इसको मूव करना
Yes.
Is it
Yeah,
okay?
yes, it's visible.
Kavita, is it visible?
It's visible, but it's not in full screen mode.
Okay, so first of all, what we do?
Hello? Hello? Hello?
Yeah, you're.
I hope it is fine, right?
Yeah, it's okay. Please proceed.
It's okay? Yeah.
Yeah, it's okay.
So thank you. Okay, thank you for inviting me for giving this talk. So this work is based on a recent piece which we have communicated to optics letters, that what happens to the cat state when you add a single photon. Now, and as you can see, now there are a lot of work going on continuous variable states. So cat state is one of them. Quite a few experiments in 2019 and 20 relating to cat state. Now, in a lighter note, this coherent state was with what happens to it when you add a photon was done in Hyderabad University, with Professor Agarwal there. It was subsequently experimentally verified. But surprisingly, this addition of a photon to a cat state we found so far, to the best of our knowledge, not much has been done. There have been some formal works, but what happens in how much changes it brings in can be best explored through Wigner function. So that is what I'm going to do here. It has been done with Gargi Tyagi and my student Orman. So I can't get into quantum computation, quantum information without mentioning Schrödinger, who invented this cat state in the context of these paradoxes, which has been bugging us since then, EPR paradox, and uncertainty, which is one of those quadrature uncertainty, as you know, is due to Heisenberg, and all this picture is due to Dirac. So he paid my. Now you will see that all of you are very much familiar with it. That discrete variables have been the ones which we have used extensively so far. IBM quantum experience, many of these things in MR, they are all based on discrete variables like qubits. Now they are realized in terms of photons, in terms of any two-level system. And of late, these optics-based things are, in combination with silicon-based chips, are also coming into limelight. So now, for example, in case of discrete variables, what you need is weak light source of few nanowatts. This is the literature which you could get. Now, when you get into continuous variables, the ones what you need is bright light source of few milliwatts. You will see quite a few experiments in 19 and 20 have been dealing with this kind of continuous variable states, cluster state, cat state. Many of them have been produced experimentally. People have been able to manipulate them. Now, measurements are this homodynamic detection, and the variables are quadrature variables. That's what I was referring to, like X and P. And you can do actually, similar kind of thing like control knot, phase gate, almost all of those things can be translated here. There are a bit of problem here when you deal with these continuous variables. For example, orthogonality becomes a problem, like coherent state, as you know, are not orthogonal. Now, so some of these gates are realized approximately, and so there are more knowledge, more error. So those kind of things one has to keep in account. But primarily, using the kind of operations which we are familiar, rotation, displacement, squeezing, beam splitter, all those things can be taken over to quantum world, and that's what people have been using. So now, whereas in case of here, we are familiar with this Hadamard controller. These are not our language. It came from essentially this, computation people. The physics people gave rise to this polymatrices, but the language was, basically Hadamard controller came from computation side. So anyway, right now, discrete variables are of course there. IBM, Rigetti, many of these things are using them. But continuous variable is very much there, you will see. So therefore, the coherent state, as you know, is classical. So next best thing would be to find out what happens to in cache state. And this, most of you are probably familiar that this cache code has been realized experimentally. So, it's you're curious to ask for the purpose of sensing, as also to see what really happens. You can actually see this wave particle duality in this cache state, which is sort of minimally quantum. So that was the thing. Now this, of course, cache state is a linear superposition of coherent state. So coherent states were discovered by these two gentlemen, Sudarshan and Bauer. Now, mathematically, if you see just a pure Gaussian, simple Gaussian, in the XP, it's a shifted Gaussian. Now, okay. Now, if you start with the vacuum state, so these are the quadratures, they will be properly normalized. So you get electric field and corresponding momenta are like X and P. And if you normalize them, they become like a single mode field. They exactly behave like A diagonal commutator is equal to 1. So whatever you learned in quantum mechanics, you can directly take over here. So now this strawberry fields are now Xanadu is available. Our students have done this simulation. You can start with the vacuum state. As you know, it's just one Gaussian located at origin. So pretty much you get this kind of thing. In phase space X and P, it is localized in both of them. Now on the Gaussian, if you act this displacement operator d alpha, which is exponential alpha a dagger minus alpha star a, you get the coherent state. And what you get is this one, shifted Gaussian. Originally it was here, now it is shifted. So again, there is the whole thing is positive. So you see in the XP space, everything is positive. So it's, it is a classical state. Okay. Now you go to, so in this X and P, if you see in properly suitably normalized one, the state is given in terms of this alpha n square root of n factorial n. Essentially, you take exponential alpha a diagonal minus alpha star a, factorize it. The second term on 0 gives rise to 1. When you factorize, you get this exponential minus alpha mod square 2, and then number state comes here. Now, in terms of properly normalized quadrature, you will find that it is like a circle. Delta x1 is equal to half, delta x1 2 also is equal to half. Alpha mod square is the number of photons. So on the average, it's the number of photons, because A dagger A average because alpha is the eigenstate of A, so it's the number of photons. So now, so this cache state was invented by Schrodinger as a thought experiment. Essentially, it emphasizes collapse of the wave function, the superposition state, collapse of the wave function. Now, I will not get into this mind-boggling scenario which Schrodinger thought about, dead or alive. But in our case, for example, cache state is a superposition of two Gaussians. You can think of it in terms of the double well potential. Each well, you will find out one Gaussian localized around that well. So in many physical systems, in case of a double well potential, what you realize at the ground state is actually the event cache state, or cache state is a fast excited state. So now, so to see the features which I am going to emphasize, it is better to go to Wigner function. You will find out there is something like interference in phase space, which will become very clear if you go to Wigner function. Just like we have seen interference in real space, this peculiar phenomena which is interference in phase space, I'll show you was first realized in the context of fractional revival, and then later on people have seen it experimentally. It has led to some very remarkable results. So now in optics we are familiar with this Wigner function. You take the wave function, displace the star part by y by 2, this wave function by x minus y by 2, and then integrate over y, you will have a function of x and p. So if you, for example, it represents in some sense, the wave function both in coordinate and momentum space. If you integrate over p, you get psi x mod square. If you integrate over x, you get phi p mod square. The phase information is here because of this unequal shifting. So this and this is a classical object. It could be negative, so it is not a probability distribution. In fact, negativity of this state is used to describe non-classicality in one way, and you will see cat state will be non-classical in that sense. Now, people have come up with smart ways of measuring the linear function. Recently, for example, I heard Radian transform has been used very effectively. So you can measure these functions, their properties. Now, cat state is non-classical because you will see linear function will be negative. Furthermore, it shows short Poissonian statistics. So in some sense, it is quantum, short Poissonian statistics. But the statistics part is tricky. I'll show you. Cat-like states, which will be non-negative, which will be negative in the linear function, can also show Poissonian statistics. So it's there are this quantum business is not very easy to understand what exactly is quantum, but you have to basically get clarified from many aspects like negativity, Poissonian, other things also. Now, okay, this this Mandel's Q parameter, it characterizes the statistics. So basically, if you can see the variance and is the mean for Poissonian, it will be 0 because variance is equal to mean, and sub-Poissonian will be less than 0, and super Poissonian will be greater than 0. So now, this as I told you, people are beginning to use this cat state for quantum computation. You will see this cat code is one of them, 2019-18 experiment. Now, one problem that arises is this non-orthogonality because this overlap is not exactly 0. So basically, as long as this overlap is small, you can sort of treat them as orthogonal. But then again, there are also smarter ways of doing. For example, if you take the phase space, if you confine yourself with a lattice, it is well known, the result is due to von Neumann, that the states become orthogonal. So it has not been seen experimentally, but there are ways. Instead of taking alpha and alpha as continuous variable, you take a lattice with alpha real m times some unit vector, alpha imaginary some n times unit vector. The area between them is pi by 2. In that case, as long as you confine yourself to the lattice, the states can be orthogonal. Now, okay, so continue. So this cat and this generalization, as you will see, particularly the kitten one also has been seen experimentally. Continuous variable state like which are analogous of discrete variable states, so-called cluster state, have been realized experimentally in a very robust manner. Now let us look at the cat state. So this is the event cat state. If you go to phase space, you will see this kind of thing, namely negativity. You can see here below this thing, this is negative, that is the black spot. And localization is here. Because we have two Gaussians, they're localized at minus a and plus a. This interference is the most interesting part. This interference part plus the negativity. So this is what we are going to use. Now this is the one which will record the change when you add a single photon. Now, okay, so this is the projection. So you will find out that, for example, this recent experiment which used it for error correction is based on this idea that you can see that if it is an event cascade at the origin, it is non-zero because these sum of two Gaussians, when you come near the origin, it will be non-zero. But the moment one photon is subtracted, because added or subtracted. Okay, just look at the odd cat state. In case of odd cat state, you will find out that the wave function will be 0. Therefore, there will be a negative region here and there will be 0 here. So this fact that this sudden shift at the origin actually has been used experimentally to, namely the parity of the wave function, that all unevenness has been used experimentally. If a state goes from this even cat state to odd cat state, you can correct it and bring it back. So this quantum error correction code in 2019 has been implemented based on this, because 2 photon loss will bring back the cat state to itself, because it is eigenstate of a square. So 1 photon loss, if you act A on the even cat state, it will take it to odd cat state. Act 1 more A, it will be even again. So therefore, if you one photon is lost, it becomes odd. Once it is odd, you can actually distinguish through parity check. So that parity check is the one which gave rise to this quantum error separation code. Very nice experiment has been implemented. Now, one problem with this cat or kitten or general sets of this kind is that they're very sensitive to environment, as is expected. And I'll show you that again there is a recent experimental paper where this hypercube state has been realized, where this phase space is quite robust. You can put a lot of information there because there are a lot of zeros, and they are also very robust against noise. So people are actually improving states of this kind, which hopefully will find use in quantum information processing. Okay. So now if you look at the general cat state, you can put a phase here. The interesting thing is this, that plus and minus are of course even and odd cat state, which we have seen. Now, if it is pi, if it is pi by 2, and for any other pi, any other phase, for example, this is Yerkes-Stoller state, which is very interesting because here it is Poissonian. So it shows negativity in the Wigner function, but statistics is Poissonian. Therefore, this phase plays a very key role. One has to be very careful about that because I pi by 2, it will give rise to an I. So if it is wave function is complex here, it will give rise to a Poissonian statistics. So things are not very, it can be surprises there in the quantum world. All right. So now let me go to this photon added coherent state, which was proposed in Hyderabad by Agarwal and Tara, which was experimentally demonstrated some time back. And what happens there? See, for example, this is alpha is equal to 0, which is essentially our single Gaussian. This harmonic oscillator Gaussian. You add a single photon, this negativity arises here. You can see here, it becomes quantum, so there's a negativity here, whereas pure Gaussian, it is not negative. As you keep on increasing alpha, you have actually displaced Gaussians. So the nature does not change, but some asymmetry is developed. You can see from here. You add a single photon, you again get negativity. Now, apart from this negativity, addition of the single photon, as you can see from here, does some kind of squeezing. You can see, there is a squeeze, it gets squeezed also. So both squeezing and negativity arises if you add a single photon to a coherent state. And this experiment, which was reported in Science, was a beautiful experiment where actually, in the cavity, the molecule or the atom lost one photon, and then that photon got, absorbed one photon from the microwave field. So, the microwave field lost a photon, and then they looked at the statistics, and it's a quite remarkable thing, that very sensitive experiment. But good to feel that this thing was done from Hyderabad University, overall Antara. So this reference is here. Now they have, of course, done a very systematic job. You can see image equal to 0. If you take Mandel parameter plus 1, which we have done it conveniently, so instead of 0, you can start with 1. So this you can see that this Mandel parameter becomes less than 0 as you keep on adding more and more photons. So keep on subtracting more and more. This is photon subtraction, not addition. Now you will realize that if you look at the paper, there are very interesting mathematical facts when they looked at the statistics. They came across this Laguerre polynomial with negative argument, which interestingly came up mathematically and studied very rigorously with its properties in Hilbert space much later. So and this thing manifested here in the statistics. You can see that one, Laguerre polynomial negative m. Okay, so as you increase more and more number of decrease more and more number of photons, subtract more and more number of photons, you see this q parameter becomes lesser than 0. All right, so now let's go to our cat state, that was coherent state. So very small value of alpha, I'm looking at even cat state, the overlap is strong. Now you see, and almost looks like a Gaussian, overlap is very strong. You add a single photon, as expected, immediately you get a negative region. So because of this parity check, you can distinguish between these two states. So this negativity. And if you look at it a bit more carefully, if you see our paper, it is emphasized. There are domains. You can see here, there is a domain here which separates this one with that one. That is actually also negativity. Now there are two photons. You can see immediately that this is negative, this side is negative. In between there is a positive domain. So this, looking at the negativity, very distinctly you can see addition of single photon, addition of double photon makes a distinction. This is for small alpha. If you increase alpha number of photons, you find that the particle nature manifests, because these two are basically localization of the wave function.
Professor Panigrahi, I think we've lost you. Professor Panigrahi, are you? Yeah, okay. You're back. Maybe you can stop your
Yeah,
video in case things are not.
I can stop my video.
Yeah,
I can do that.
that
How do
can
I stop my video?
save your bandwidth.
How do I stop my video? How do I stop my video? My video only.
Video only.
Audio. Mute the video. Stop the video.
Yeah, it's fine.
Yeah. So now, so in some sense, you can actually sort of see some kind of duality here. Particle, small alpha, basically less number of photons, and these are the kind of things which are useful for QKD, because you can create wave packets with very less number of photons. So here you cannot distinguish between the two Gaussians, or uncertainty is very high. Here, as you keep on increasing alpha and more number of photons, you are able to distinguish them. But at the origin, where the negativity is there, you get the this interference pattern. So as if the wave nature and the particle nature were able to sort of distinguish them in the phase space. So now in this is case of two photons, as you can see, this shift here it was red here, and immediately here it is blue. So the shift is a very measurable quantity. Now two photons, again, this phase shift is very clear, and this interferometric way of, since the original function is measurable, you can actually interferometric way, you can actually sense the photons, that this can be visualized. Furthermore, you see the squeezing, that you can see here, that the moment you add a photon, the squeezing becomes very clear, as if there is some repulsion. So two photons, there is more squeezing and spreading out. So this thing, which was, of course, coherent state would not show this kind of interference pattern. So this is the single greatest advantage of having a flat state, that interferometrically one will be able to measure addition of single photon. And as I told you, parity measurement has been done. The moment it shifts from even to odd, you can immediately distinguish that, because at the center there's a negative domain which develops. So they whereas this interferometric means was not available in case of coherent state. Okay, so now look at the statistics. For example, you will see there's a distinct difference in statistics, and we have added +1 to make it clear. Geoff-Stoller state, the last one, which was 1, namely q is equal to 0 was Poissonian earlier. The moment you add 1, it becomes negative. So statistics also shows the difference, but measuring through statistics would imply large number of photons, whereas this coherent state, sorry, the original function can be probably directly measurable. Okay. Now let me show you some of these things which people have seen experimentally. See, for example, this is the experiment which was 2019 experiment, yeah. And there, yeah. What do I do? How do I remove this one? Yeah. I think it would be. So you can see that. So what they did is that they have a coupled, system. There's a cavity here. This wave packet which comes in. So therefore, the initial input is cavity with a Gaussian kind of wave packet, and then it's a coupled system of a qubit. Basically, this system is like a qubit coupled with radiation. So therefore, and the qubit is taken to a superposition kind of thing. When it is a superposition, or the original either this or that, the moment it becomes a superposition, you create even and odd cascades. Then measurement, if the measurement outcome is this, that leads to even cascade. The measurement outcome is 1, it leads to the odd cascade. So it's coupled system of qubit with the radiation field in a cavity and measurement that leads to creation of this kind of states. So this was the trick which was used in 2019 by hacker et al. Now, let me tell you the paper which is a very profound paper that which got me into this area of subplank structures. You saw this interference pattern. Now, if you go to Keaton state, namely 4 things, you will see there is this structures which arises in the wave function, in the linear function, which has an area less than Planck's constant. You may ask, does it have physical meaning? It was shown by Jurek in 2000 that indeed it has physical meaning. So let me show you that. So this is what as expected, for example, Keaton state, which is localized both in coordinate space and also in momentum space. We'll have these 2 Gaussians here. Momentum space localization is essentially coordinate space localization when the parameter is imaginary. Suppose if you have x minus a, it will localize here. If it is x plus ia, it will localize here. So real space, if you take a wave function, which is, you can actually create the states which have been created also, localized in 4 places. But look at the interference. There is interference, between these two. There is interference between these two, and there are interference here also. End result is the origin, which is being shared by all of them, has structures which is subplank. So if you, for example, look at this nature paper, you will see that there are zeros here, and this area bounded by the zeros has subplank structure. You can actually show its area is x bar square by a. A is the support of the Gaussian. So indeed, so now the question is, what is the physical meaning of the subplank structure? What Jurek pointed out, that they are actually useful for quantum metrology. He showed that you can use it for realizing Heisenberg limited metrology, namely sensitivity can be increased. Furthermore, his point was that these structures, when you keep on putting more and more Gaussians, will lead to quantum chaos. So quantum chaos part people have not checked, but people have actually experimentally done this kind of thing using laser. There, it is not Planck constant, it is lambda. So 2007, there was an experiment, by this group in Poland, which realized this experimentally, the CAT state. The so-called Keaton state was realized, I think, 2016. It's a paper. Since then, many people have realized it in laser, and this interference have been seen experimentally. So the subplank structure has physical meaning, and they are actually tiles, very nice tiles. You can see here, all these rays are actually zeros. Now, so I pointed out to you the error correction code. Now, this CAT code also has been seen experimentally by this group in Yale, and which is basically, you can know what kind of quantum operations that can be used has been demonstrated. You can see here again, first you create the states, localized states. This is the phase space structure. And after you create the states, the tomography shows the presence of the states. So, and you can show that they are robust against 2-photon loss. Okay. Now, this it was pointed out that both this CAT, Keaton, all those states are very problematic states because they are not very robust against noise. In that
Professor Panigrahi, I think your slides are frozen. Hello?
is it?
Yeah, okay. Yeah, now it's okay. Now it's okay.
Okay. So how much time I have? 5 minutes?
Yeah, around 5 minutes. We seem to have lost you again. Hello?
Yeah.
Yeah, now you're back.
Yeah. So there is a bit of problem here. Now you may wonder, this kind of subplank structure, do they appear in other places? Answer is yes. In fact, if there is a wave function, there is a Hamiltonian whose spectrum is n square, like in Morse potential. In molecular wave packets, you do see them. They have physical implications, for example, in terms of molecular bonds stability. So there it is not very clear, just like Jurek showed in his Nature paper, but you do see soft Planck structure there. Okay. Now, as I told you, that ketone state also has been seen experimentally. Here is the experiment, and this experiment is a pretty recent experiment. So in fact, you can actually now looking at the stability, you can check that you can design certain potentials where in certain parameter domain they could be very stable. The hypercube is one of them geometrically richer, but in case of using a suitable potential, also you can do that. For example, here you can see that these things are very stable. If you take suitable kind of design potential. Now you may ask that so far we have done for pure states. What about mixed state? Answer is yes. That in mixed state also it can be used. So this is what has been shown. I will not get into details, but you can check it out. That mixed state, this kind of structure survives. Now another thing is that when it comes to quantum metrology, we have seen this Heisenberg limited thing, but there is this concept of weak measurement. Interestingly, there is a deep connection between soft Planck structure and weak measurement. Both of them arise due to interference. You can see that when the interference
I think we've lost you.
I'll just wind up
Yes,
a couple of minutes more. Now there are, as I told you, cluster sets have been generated 30,000 entangled modes. These are all recent results, and this parity check detector I was telling is this experiment 2020, and now this time domain multiplexed cluster state is the reference given here, pretty complex ones. Now this most the news everybody knows now, that how big is this thing, Clyde-based quantum computer is a matter of great pride for China. Now this is the other supremacy, which again is a big news. Now many other light-based breakthroughs have already come, so I will not get into that. Okay, so now slowly we are getting into technology now. Hopefully many of these things will play a key role there. Okay, I think I will stop here. Thank you for your time.
So thank you very much, Professor Panigrahi. The floor is now open for questions. In the interest of time, we'll restrict it to 1 or 2 questions. So could you please raise your hand and I'll get to you. Those who want to ask questions, please raise your hand. Yeah, so I see a question by Thomas Conrad. Thomas, please unmute and go ahead.
Yes. Hello, Professor Panigrahi. Thank you for your talk. Hello. I wanted to ask, since you mentioned this sub-Planck structure, is this in any way related to super oscillations? Because I believe that you are doing this with wavelengths that that are not too small. So since you have such a structure that locally shows higher oscillation frequencies, is it super oscillations, and can we use it to encode signals and send signals that are that transport much more information than the Fourier spectrum would allow?
See, that's a very nice, very beautiful question. Very recently, like a couple of years back, there was a rapid communication in physical way, a very short 3-page paper where they have shown this has relation to super oscillation. Professor Michael Berry was here. When I told him, he said, no, it is not related to that. But I did not pursue it. Very recently, I forwarded you that paper. And in fact, that is a very interesting question, that can we really, use it for transmission of more information? That's a very good question. I'll think about it. I can't answer offhand, but looks tempting. It should be possible. But that other paper, I'll forward you that other paper.
Oh, that would be nice. Thank you very much. Thank you. Bye-bye.
There's a question by Anirban Pathak.
Yes. So am I audible?
Yes, you're audible.
It's less of a question, more like a comment. Means in similar situation in cat state, because when they superpose there are many holes which are created in photon number distribution, and a hole in photon number distribution is a manifestation of non-classicality. And the same thing is happening when you are adding photon. If you add one photon, there is one hole at n is equal to 0. If you add two photon, there are two holes, and holes in photon number distribution is always P alpha is negative.
Okay, very nice, very interesting. Yeah.
So that will definitely show non-classicality, but whether a particular witness will see it or not, that's a different issue.
Is it measurable? I mean, is it easily measurable?
Photon number distribution means is measurable in some sense.
Okay. Yeah, thanks. That's a very interesting observation.
Arvind, please unmute.
First of all, Prashanta, hello, and thanks for accepting our invitation and giving a talk.
Thank you.
Continuing on what Anirban said, there are these very interesting local conditions on photon number distribution, which can tell you whether it is classical or non-classical. I will send you, we published these papers quite some time ago. One of the results is actually not even published, it's on the archive, we never published it. But the point is that you can have local conditions. If you give me Pn plus 1, Pn plus 2, just 3 probabilities for finding n photons, n plus 1 photons, n plus 2 photons. From here, I can construct a condition for non-classicality, and that then will be valid for all n. So you can have infinitely large number of conditions which are based on local fluctuations in photon numbers.
Oh, beautiful.
So it will be interesting to connect with.
Yeah. So you are talking about Arvind, you are talking about Kliskos criteria, or it's something different?
Well, I'll send you. We have a fully detailed, worked out.
There is something called Kliskos criteria, which is similar.
No, it is not that. These are called local conditions on photon numbers.
See, local condition would be experimentally much more interesting.
Yeah. So just three Pn plus 1, Pn plus 2. You can write down an inequality.
Okay, thank you. I look forward.
Thank you.
Yeah, so I don't see any more hands raised, but if you have any questions, you can, type it in the chat box, and Professor Panigrahi will get back to you after having a look at them. So I now thank Professor Panigrahi for accepting our invitation and giving this very nice talk. We now move on to the last talk in this session, which is by Professor Anirban Pathak. Anirban doesn't really need an introduction to the quantum community, but for the sake of the students, I will go ahead. Professor Anirban Pathak is a theoretical physicist who did his PhD from Vishwa Bharati Shantiniketan. Subsequently, he was a postdoctoral fellow in the Freie University Berlin. He joined JP Institute of Technology, Noida in 2002. At present, he is actively involved in teaching and research related to several aspects of quantum optics and quantum information, with a focus on quantum cryptography. He's a fellow of the National Academy of Sciences, India, and Institute of Electronics and Telecommunication Engineering. He's also a member of the editorial board of Quantum Information Processing. He's a recipient of the 2017 Shri O.P. Bhasin Award in the field of electronics and information technology. So Anirban, the stage is yours. You have about 30 minutes for the talk and 10 minutes for questions.
Okay.
Yeah, Anirban, can you pull the screen little? We can see only half your face. So can you just pull the laptop screen or move back a little? Yeah, that's it. Okay. So welcome.
Thank you for introduction, and thanks for inviting for the conference. So I would like to give a kind of odd talk. Means I'm a quantum cryptographer, but I want to become devil's advocate. Means I want to talk about some weaknesses of quantum cryptographic protocols, and I want to stress on certain aspects which are less spoken but are probably important. So this is something in the left-hand side where my mouse is. It's showing a product which claims that they will give a quantum cryptographic solution to the end users who are using telephone. So the telephone is supposed to be a classical thing. And recently Samsung also claimed that they will have a quantum random number generator in their phone and will provide a quantum cryptographic solution. So for a while, there is an attention about that the end user can be classical. So I'll talk about this question mostly, that whether an end user can be classical, or in more appropriate language, clone Q, who is a classical user who can perform classical operations on quantum resources. So identifying heat from a completely classical user, so apply classical operations on classical resources. So we continue. So this is the glimpse of the things which I wish to discuss as time permits. Maybe I'll not be able to provide equal stress on everything. So for most of the time, the discussions on quantum cryptography is focused on QKD, quantum key distribution, but QKD is only a particular aspect and which is not even an application. It's not even an application in the sense that if you just have key, that's nothing. Means with the key, you have to finally send some communication. You have to communicate a message. So you have to encrypt the message and send it. So there are direct communication routes like quantum secure direct communications and the control version of that, which is a third-party controller. Usually we call it Charlie. When he allows, then Alice and Bob can communicate. There is a specific version of it called deterministic secure quantum communication. So the difference is in QSDC, Alice and Bob does not need any additional qubit for exchanging information, but in DSQC they need. But in both of them, the common thing is that they don't need a prior generation of key. So in that sense, these two are complete application, but QKD is not. So QKD, after QKD, you have to go back to your classical encryption technique. You have created a key, you encrypt, you decrypt. But these are completely quantum in the sense that you are not generating key and you are doing direct quantum communication. Well, now come back to whether is it really fully quantum? So again, even for QKD, a very important phase is authentication. And in authentication, you need a kind of private key which is to be shared beforehand. And quantum key distribution is essentially a key amplification scheme. And the authentication has multiple issues. So apart from QSDC, DSQC, and their control version, there is something called QKA, Quantum Key Agreement, where Alice and Bob equally contribute to each digit of the key. And in most of these schemes, means if I want to go a bit ahead, in most of this scheme, there is a semi-honest Alice and Bob. So this is the untold assumptions that Alice and Bob does not want to cheat, and they follow the protocol honestly, and remaining within the protocol, they try to cheat each other or the scheme. So there are some are superset, means if you can do quantum secure direct communication, you remove the controller, you will be able to do QSDC. If you can do QSDC, so that then you can essentially do QKD, because instead of a meaningful message, you can always send a random message. Then there is something called quantum dialogue. Quantum dialogue is a more powerful protocol where Alice and Bob both can communicate with each other. So these are the post-QKD schemes, which are probably less discussed, and they have hierarchical version also, where all the users are not at the same footing. So when you try to implement all these things, so one thing which automatically comes that any QSDC schemes or DSQC schemes require quantum memory, and quantum memory is not available at the moment. And here is a point to note that even in BB84 protocol, if Bob had a quantum memory that can be converted into a direct quantum communication scheme, because Alice can consider that half of the BB84 string, which is prepared in 0, 1, plus, minus. So this is actually made up of true string. One string he has put his encoding, and in another string, in half of the string, which are randomly placed, are used like a decoy qubit for BB84 kind of checking that whether eavesdropping is happening or not. So in the rest half, which is stored in Bob's end, some message has been encoded. So if it is 0, then it is 0. If it is plus, it is 0. If it is 1, and so meaningful zeros and ones are in those. But only if it is passed in the eavesdropping check, then he discloses that which qubit has been encoded in which basis. And since then Bob knows the basis, Bob can take out from his memory and do measurement and do direct quantum communications using BB84, using BB84 subroutine, provided he has memory. The memory is a strong requirement, and we don't have memory. The other thing which comes again and again is called particle order permutation. So this is a trick which cryptographers use, and I do use it. I often write papers with particle order permutations, but nobody knows which optics can actually do this particle order permutation. So I'll come back to this again. So the whole idea is that suppose you start with a sequence of Bell states. So you prepared n copies of Bell states, and then you randomize the particles. Like you don't know that particle 1 is entangled with particle 2 or it is entangled with particle number 30. So Eve does not know that which one is entangled with which. So if it does a wrong choice and measure two particles which were not initially entangled, then that will lead to entanglement swapping. So when the sequence will be disclosed by Alice and Bob will do Bell measurement on the right pairs, then entanglement swapping will show the lead to, suppose you start with n copies of Xi plus, now you will find phi plus, phi minus, Xi minus everything, and you will be able to identify eavesdropping effort. So now you see that in this particle order permutation kind of trick, we are only using orthogonal states because I'm starting with Bell states. I'm just making it swapping. And final measurement is also on the Bell state. So essentially the feeling that QKD happens because of our inability to do simultaneous measurement in two non-orthogonal bases is not required here. In principle, we can do everything in using orthogonal states. And for all those events, except some of them, many of the protocols uses particle order permutations, and nobody knows that how to do this particle order permutation. So here is a violation of a cryptographic policy. So the policy is that Alice and Bob is restricted by the laws, by the materials available in the present technology, but Eve is not. That's why photon number splitting attack is possible, but you cannot use it in other way around, and Alice cannot stop the multi-photon pulses and allow the single photon pulses to go. Then you have a single photon source. So why Alice is not allowed to do that? Because that's not available in the technology, but in many protocols we use POP, which is not also available in the present technology. Then there are issues with the detector mismatch attack, possibility of Trojan horse attack. These are some aspects which are less discussed. So I skip those things like repeater, single photon source, single photon detector issues. And here is a brief that we have to talk about authentication issues, hacking possibilities, problems with finite key size. So most of the security proofs are with the considering that the key is asymptotically big, effect of noise, especially Markovian noise and non-Markovian noise, and the possibility that Eve hide behind the noise, composability issues, secure multi-party computation. Very less is discussed about secure multi-party computations, and they are very important. So from the next slide, I will actually start from an example of secure multi-party computation. Then semi-quantum things where the end user is classical on quantum or clone Q, and the orthogonal state-based scheme. So I will not be able to give good weightage on everything, but I'll try to give glimpses of this kind of issues. So the whole thing started from a very nice paper of Lowe. So where before that, when BB84 and such things appeared, people started thinking that all cryptographic tasks on the earth will be able to be solved by quantum resources in unconditional manner. So this kind of omnipotent idea was first questioned by Lowe, and they show that there are tasks which you cannot do in two-party scenario, you will require three-party scenario, and they defined a task which are not restricted to communication. They are more of like a computation. So if you have to compute a function f of ij and is equal to 1 if I is equal to j, and f of ij is equal to 1 if I greater than j, and f of I j is equal to 1 if, sorry, I shorter than, else is equal to 0, sorry, it may be shorter than or greater than means. So this is a kind of comparison that you have been given two functions, I and j, and you have to calculate that whether I and j is equal, and if I and j are not equal. So this is called, this has a particular name, this is called socialist linear problem, and a generalization of that is quantum private comparison. So you have two people are giving these inputs I and j, and somebody else will compute function of ij without knowing I and j. So this is the important restriction, that he will not know I and j, he will just know that whether I is equal to j or not. So this kind of task is called quantum private comparison, socialist millionaire problem. So socialist millionaire problem's idea was that there are two millionaires who wants to compare their assets, but they don't want to disclose how much assets they have. So this kind of problems are also called post-Cold War problem, where say two nations want to destroy their nuclear weapon in equal number, but nobody want to disclose how much they want to destroy. So they want to come in a number which are equal. But so they wait till the simulation gives you f of ij is equal to 1. A particular important task of this kind is voting. So this is a few years back, maybe 2 years back, a party ruling in Delhi claimed that the electronic voting machines can be tampered. So IT Quantic successfully sold a voting solution in 2007. So this is a particular kind of secure multi-party computation. So we work on this, but without going into detail of the theorem, I just want to note that we have a theorem which claims that you cannot have an unconditionally secure voting. You can increase the confidence on your voting systems, but it can never be self-consistently unconditionally secure. So if it satisfies, there are a couple of criteria. If you satisfy, and there is a kind of trade-off. If you want to satisfy three of the criteria, then fourth will not be satisfied, and so on. Anyway, so this simple criteria is simple voting mechanism started with a qubit. So we start with a qubit, entangled qubit like this, and one particle, say you have 0, 0, 1, 1, 2, 2, and one particle of this is sent to the first voter. If he wants to vote yes, then he adds it and k become k plus 1. And if he does not, then it just unchanged and it goes. So if he votes one vote yes, then it will become 1, 0, 2, 1, and 0, 2. So then it goes to the next voter, and next voter may also decide to vote or not for yes or no. So this is a kind of voting called binary voting. And finally, the tallyman measures both the qubit. So one particle was with him and the other particle which is coming from all the voters, and then find out the difference. And it should be a modulo n operations, and depends what is the value of n, that will depend on the number of voters. So this is a very easy protocol to follow. And just we want to show that these are the kind of problems which we can do, and which are not that much discussed, and which can be used to, say, enhance our democracy. Then we can have quantum auction, which is also a computational problem, which risks security. And if we can use quantum technology to provide a secure auction, then probably in countries like ours, the many of the corruption issues can be handled with quantum technologies. So anyway, so this we want to go briefly, that every time that we do about QKD, there is a general structure that Alice and Bob communicate with each other. There is a send a random signals over the quantum channel. They perform test of check whether eavesdropping happens or not, and so on. But there is a requirement, that ability to generate a truly random bit string through a physical process. But there are some inherent assumptions which we speak less. So Alice and Bob are honest, actually semi-honest, that they follow the protocol, implying that both of them strictly follow the protocol. Alice and Bob can exchange classical message authentically. So these things are questionable. So here is an authentication scheme. So how to authenticate? So most of the time we write a protocol by saying that, so Alice verifies authenticity of Bob. So a major problem is here, and many of the protocols of quantum authentication are actual events. There are two kinds of things. One uses hash functions and shows certain confidence on hash functions, but that's not, hash function itself is not unconditionally secure. So if your authentication is not unconditionally secure, you cannot claim your QKD is unconditionally secure. So here you need at least some pre-shared bits, and the question is how those e-bits or quantum bits will be shared previously. So if that cannot be secure, because rest of the QKD is similarly actually a key amplification protocol. So once you can authenticate, you can create a 100-bit key and then keep 10 bits of them for next time's authentication, and so on. Then the point which I was stressing it from the beginning, that QKD itself is not an application. Application stands over the QKD, and authentication is in the base. So one option is that we forget about QKD and we start on the application itself. But again, that would also require authentication. So we cannot get rid of the authentication issues. Then usually the demand is that, say, the key should be correct, that if it succeeds, then Alice and Bob must have the same key, SA is equal to SB. Secrecy, if the protocol produces a key, that is, it's not a null set, then SA is uniformly distributed and independent of the state of the system of if or any adversary. And robustness, if the adversary is passive, then there must be a key. Now, these are the general ideas, and actually you don't work with the ideal system, you work with the real systems, and not only the side channel attacks are possible. There is a question that how close is your real systems to your ideal QKD systems, and we have a P ideal and P real, but we don't want to go in the mathematical language. I just want to know that if they are close by a number called epsilon, then as far as the security is concerned, that's called epsilon secure. But now I have a network of things. So many people are talking about quantum internet or quantum network. So if I have three parties, Alice, Bob, and Charlie. So even if Alice and Bob is epsilon secure, say its security parameter is epsilon 1 and Bob to Charlie is epsilon 2, it does not mean that Alice to Charlie is secure. So if I can prove that if Alice to Bob is epsilon 1 secure and Bob to Charlie is epsilon 2 secure, and then Alice to Charlie is epsilon 1 plus epsilon 2 secure, then it's called composable. So in other words, that if there are 3 points, multiple points, the point-to-point security does not mean that it connects the other point also. So if there are small networks, small paths in a network, individual security will not prove the security of the entire network. So composability is an issue which is needed at the moment where to discuss in detail, because we are approaching things beyond QKD where quantum internet is so often discussed. So if you have to say that my protocol will work for quantum internet, you have to come with a composable security proof. So composability and finite key size is certain issues less discussed but very important at the moment. Now, well, there are some spatial basis, which is, so this is a cartoon where a teacher asks a student that give an example of quantum superposition, and a student tells that marmot, which is a half fish, half girl. Then the teacher told that nobody has seen, and student is answering that, well, when you measure, it collapses to fish or the girl. The teacher said that, oh, it's not correct, because there should be a basis in which marmot itself is an element. And if you measure in that basis where marmot itself is an element, you should get marmot as marmot. So that's where classical stochastic theory is different from quantum theory, and the trick of the cryptography is here. So even if I have an orthogonal state, but somehow if I have to get the exact state, so that particular state must be a basis element, and I must be allowed to do a measurement in that basis. So by hook and crook, if I can create that basis is not accessible to Eve, then even with orthogonal state, I can make quantum cryptography. So this is one such example. This is called Goldenberg-Hedman QKD system. So here is a state which is Kate A plus Kate B by root 2. And another alternative is Kate A minus Kate B by root 2. So Kate A plus Kate B or Kate A minus Kate B depends on whether the signal is coming from this side or signal is coming from this side. So if I call that the upper path is A and lower path is B, so Kate B is waiting here, and Kate A is going fast, and Kate A is waiting here. So there are 2 packets, but the 2 packets are never available simultaneously in the channel. So as if Eve is bound to measure which path information or particle nature, because Eve has to do the measurement in Kate A, Kate B basis, but Alice and Bob can do measurement in superposition basis or like a wave-like basis. So as if Eve is restricted to particle property and Alice and Bob can do wave property where A plus B and A minus B is allowed. So it's an orthogonal state basis scheme. There is another scheme called NV09, N09, No09. So there are a couple of them, and many of them has been experimentally realized also with Marco Genovesi and others. So we come up with the idea that, well, we can start with, instead of this kind of things, means where time synchronization is very important, you can get rid of time synchronization, and you just can use a trick which has been used by Long and Deng and others, many Chinese groups for long, that you start with a set of particles and you do particle order permutation, which is called POP. So we thought that we start with Bell states and change the order of the Bell states. So I make a randomization operator or permutation operations and send it. So even if I encode some information in them, if I'm checking, say I'm doing a eavesdropping checking, and I mentioned that, well, after Bob receives all the particle, Alice tells that first qubit was entangled with the third qubit, and they do the Bell measurement involving first and third, second and 30th, maybe third and 44, and so on, means whichever is entangled with which one. But since Eve does not know which one is entangled with which one, any effort of eavesdropping will lead to entanglement swapping, and that will be detected. And this can easily be, now you use that this sequence has some particles which are actually carrying message, and some particles, some Bell states are decoy qubits. So we published many papers, and here is a list, and we show that almost everything that you can do with BB84 kind of things, or using 2 or more non-orthogonal basis sets, mutually unbiased basis. So you can do same things with them. So we mentioned in line of GV that this is called Goldenberg-Vedman subroutine, and the standard one is BB84 subroutine, which are ideally same. So when there is no noise, they are equivalent. But what happens in presence of noise? So we have checked in presence of non-Markovian noise as Markovian noise, etc. So here we show that means in presence of noise, it's not same. So, and again, if you want to apply GV subroutine, it would depends on whether you are using Chi plus minus or Phi plus minus, which entangled states you are taking. Ideally, everything is same, but their effect on noise is different on different entangled states and different on BB84 protocols or BB84 kind of subroutine and GV subroutine. So the point we want to make is that even if something is shown to be equivalent in ideal scenario, it may not be equivalent in presence of noise. So now I want to go to something where end users can be classical. So there are 3 possibilities: that the end user has all quantum capability, so then he is a quantum user. There is a possibility that end user is classical. He operates classical operations on classical resources, and there is a clone Q. So we are interested about this kind of user that is classical on quantum. So a classical user can do a measurement in 0-1 basis on quantum resources. So he can do measurement on entangled states or superposition states, but he neither can prepare entangled states or can keep a quantum random number generator. So it's a restricted classical user, and using that we can do many things. So applications beyond semi-quantum key distribution. Semi-quantum key distribution was introduced by Talmor. Then we have talked about semi-quantum secure direct communication, semi-quantum e-commerce, semi-quantum private comparison, etc. And now we are interested in something called delegated verifiable quantum computing. The idea is that, like this, IBM and many companies, DOF and all these people are giving you cloud services. So some are free, but when you are buying it from your money, then you will be able to know that, well, you are a classical user, you have a conventional computer that you throw the job. So are they really did it in quantum computer, or it's a strong classical computer which has done it? So that's verifiability. And another thing we want to do is that they will not know my job. So can I delegate a job? He will perform the task for me without knowing what research actually I am doing. So is it, I mean, we don't know the final answer, but these are the interest where cryptography is. So we want to talk about semi-quantum protocols. So where the end user is a classical on quantum, in the sense that he can do either, if I'm sending a qubit, either he can do the measurement only in Z basis, or he just reflect it back. So things will be clear from this protocol. So this is not my protocol, but this is easy to visualize. So this is a Talmor's protocol. So Alice starts with, as before, like BB84 protocol. She creates a couple of qubits in 0, 1 and plus minus and sends it to Bob. So Bob can do 2 things. Bob is a clone Q. Bob can reflect it back or measure it. So R is for reflection, M is for measure. And when doing measurement, being classical, he cannot do measurement in superposition. He can do measurement only in 0, 1 basis. So this happens after measurement or reflection, it is returned back. So when he measures, and if he gets 0, he returns 0. If he gets 1, he returns 1. So there are 4 possibilities. If total n particles were sent, or n photons were sent, n by 4 cases are 1 in which Alice prepared Z and Bob does measurement. N by 4 is that Alice prepared Z and Bob returned. Bob just reflect. So all the reflected cases, Alice should get back, and after receiving all the thing, Alice does the measurement on the same basis. So the trick is that if no eavesdropping has happened, so Alice should get back the same states in this situation. So after receiving everything, Alice measures all of them in the same basis in which she has prepared. So if the first qubit was prepared in Z basis, it is measured in Z basis. If the third qubit was prepared in X basis, it is measured in X basis. So in this cases, it should be same. When it is measured, prepared in X basis, and since Bob cannot do X basis measurement, so those things are ignored. And if it is Z basis, so from this cases, I will get that whether eavesdropping is happening or not. And from this will create my shifted key. So this, as you see, that here the Bob does not need to have any kind of quantum capability. But Bob, so the question which is unanswered here is that Bob needs a random number generator because he needs to do the measurement in random way. So whether a classical random number generator will be enough to justify the claim for unconditional security or not. So finally, the n by 4 leads to 2n qubit, and Bob, they disclose half of them and to check the error rate, and n remaining are the shift bit, and then you apply privacy amplification, etc. So now we talk about quantum private comparison. So quantum private comparison is a particular kind of protocol. As I mentioned, that Alice and Bob gives their input, or you can think of socialist millionaire problem, and third party or TP is the third party who will compute, and he will not know the input. So third party will not know how much asset Alice have or how much asset Bob has. So he will only know after doing the computation that whether they have equal assets or not. So that starts with 8n Bell states. So 8n, that's a particular, there is no reason for writing it 8n, because then at the end, I just want to compare n bit of information from Alice and n bit of information from Bob. So start with 8n Bell states, and these are created in Xi plus or Phi plus. So you could have created in Xi minus or Phi minus, does not matter. We just need that the parity should be different. So this is a parity 1 states, and suppose this is a parity 0 states. So this parity will play important role in the last step. So TP sends the two sequences, SA and SB. So SA is made up of all the first particle, and SB is all the second particle, one to A for Alice, one to Bob, to clone Q users, Alice and Bob. And as before, Alice and Bob can do events. So if there are 8n Bell states, there were 16n particles. So 8n was sent to Alice, 8n was sent to Bob, and they randomly return half of them and randomly measures half of them as before. So there are 4n qubits. So both the users measures half of the received qubits, 4n qubits, and there will be 4 cases here. So what are so after receiving the qubits from Alice and Bob, TP performs Bell measurement on the received pairs. So a particular measurement will yield one of the Bell states, and if TP's measurement yields the same Bell state as was initially prepared by him, he announces 0, otherwise he announces 1. So this will be, so all the cases when Alice and Bob both have returned the qubit, TP is expected to get the same Bell state. So 4 cases as before happens. So both Alice and Bob reflect the incoming qubits undisturbed. This case is useful in sharing key between Alice and Bob. Sorry, but it can be used to eavesdropping. This case is, sorry, here is a knot is missing. This is not useful. So if Alice and Bob both reflect, then TP should get same Bell state what she has prepared. If Alice and Bob measures the qubit while the other party reflects it, all these cases will be discarded. This is not useful. So the useful cases are those. So these are the case 1 is useful for eavesdropping chipping, and case 4 is when both of them has measured are useful for communication at the later. So after announcement of TP, both Alice and Bob discloses the coordinates of qubit they have measured. So if you just disclose the qubits you have measured, means it is automatically disclose the qubits which has not been measured. So in those cases, if Bell state is matched, the initial Bell state and the final Bell state, then we know that eavesdropping has not happened. Now, in these cases, Alice and Bob must have a correlated beam, correlated sequence, but they don't know whether they have the same qubit or they have the opposite qubit, because they don't know whether TP had prepared Xi plus or Phi plus, 0, 0 plus 1, 1 by root 2 or 0, 1 minus 0, 1 plus 1, 0 by root 2. So they may have the opposite bit value or the same bit value, but they themselves created a key and they just do this kind of operations that. So they have a secret. Suppose Alice's secret or the assets is MIA. So with that, he does XOR of KIA and XOR of KIAB. So KIAB is the key between Alice and Bob. So this inclusion of this key between Alice and Bob, which can be done by using the previous protocol, which I mentioned, which ensures that third party will not be able to decode and read what is the value of the assets of Alice. So now this thing goes to the third party, and third party, both Alice and Bob sends, third party XORs this with the parity of the initial state. So parity will take care of this KIA and KIB are same or not. So if parity is CI/CAB plus the parity value 0 and 1 when it is XORed, and if it gives you 0, that means they have the, for all value of I, that means they have the same amount of asset. So we can do in a semi-quantum manner. So we can do many other things in semi-quantum manner. So I'll just show glimpses. So control, direct, secure semi-quantum communication is possible, and control, direct, secure semi-quantum communication, wherever it is possible, any schemes which you can design for control DSQC, you can actually take it for, actually this is the structure that there is a Charlie who can be viewed as a quantum online store, and it can be read to quantum e-commerce. So he prepares a GHE like state, creates, sends a sequence to Alice, which is a conclave and buyer, and a Bob is a merchant. So these are practical situations that the bank may be a rich resource and bank can have quantum resources, but a big bazaar or such a place from where you are buying something, they may be a classical computer and you may be a classical computer, but still you can take the advantage of quantum computing and do unconditionally secure things. But only thing is that things will be slow. The number of qubits which you have to start is large number, and then you will get a very smaller number of communication. But that cost is acceptable, and we can do semi-quantum e-commerce schemes, and that's a modified version of. And in principle, if you have any schemes for controlled deterministic secure quantum communication, be it semi or semi-quantum or not, you can convert it into quantum e-commerce. So what is the problem? The problem is that any such schemes require a memory. And say, when I was telling this kind of protocols, so one has to prepare the Bell state. One qubit has been sent, so other qubit has been stored by TP and later is doing the Bell measurement. So it requires quantum memory. So how this has been experimentally realized? So there are experimental realization of DSQC and QSDC, and mostly it is done by Long's group. So what they have done, so they have actually, instead of using quantum memory, what they have used is called delay. So delay means you delayed all the qubit by equal time. So say 5 seconds or 10 seconds or 5 microseconds. But a memory means if I need the first qubit later and second qubit before, or I decide in between that I will take the third qubit, I can take it out. But that was not possible. So most of the experiments which has been done so far on this kind of direct quantum applications, they have been using delay in place of quantum memory. Regarding the semi-quantum experiments, there is a much development in the recent past, and initially there was a proposal which has been criticized, and then semi-quantum cryptography, it's at the key distribution level, has been done by Talmor and others. And there is one from the last year, which is yet to be published. Now, I will not go in detail of, the time will not permit, because the same kind of task you can do with the orthogonal states also. You have to start with the n e-pair pairs and use some of the Bell states as the decoy. And for that, you don't need any kind of parity. It can work in any Bell state, because it will actually entanglement swapping leads to that. So these are some aspects. And of course, what Arvind is also interested, continuous variable cryptography is another aspect which needs much more attention, because of the fact that now people are talking about metropolitan quantum network. So if you just want to make a quantum network, you will require composable security proof. At the same time, the continuous variable works better for a short distance as far as the if you compare with the noise. And this is a short talk, so I have not included everything, but a very nice approach to all these things can be TF-QKD, a twin field QKD, which has all the beautiful features of MDI QKD, but which is less resource sensitive. And now there are experiments on TF-QKD also. So we work on certain aspects of cryptography, continuous variable cryptography. We converted a B92 protocol into continuous variable B92 protocol. As before, we have worked on continuous variable DSQC, direct secure quantum communications, and quantum dialogue. So quantum dialogue is a mean in which Alice and Bob both can talk to each other. And then regarding the security, so before I disclose, I just want to talk some small things on the security aspects of the hacking probabilities. So normally the things which we have in hand at the moment are capable of doing individual attacks, where each ancilla qubits interact with the qubits which is going from Alice to Bob, and you measure them individually. A more powerful attack is a collective attack, where you can do a collective measurements, and the most important attacks are most powerful ifs are who can do a collective operations on ancilla, which we have written as UP, and you can do collective measurement as well. So although at the moment I cannot do beyond individual attack, so security proofs, practical security proofs should consider coherent attack as a possible option. So there are many papers which has been published recently, which are to some extent can support collective, are safe against collective attacks, but there is no discussion on the security against coherent attack. So there are tricky things as before, so this part is the easiest part to follow. This is a nice example of quantum attack, because quantum cryptographic protocols are ideally secure, but in reality you have to implement with the devices, and devices may have imperfections. So this is a quick attack which we can show even in first year, even to first year students. So there are 4 light emitting diodes, laser diodes, and 4 laser diodes which are using the 4 sources, and there are polarizers. So one is giving vertical polarization, horizontal, anti-diagonal, diagonal, and we are mixing up before sending it. Now Eve sends a intense pulse through a circulator, and circulator is a device which takes, if it comes from 1, it goes from 2, and so on. And if it goes through this, since this is vertically polarized, so all things, entire light goes here, and this changes its intensity. If its intensity changes, wavelength changes, and this become a new wavelength, lambda 3. In this case, 50%, none of the light goes inside because this is perpendicularly polarized. It's simple Malus law. So no change in the wavelength. Lambda 1 remain lambda 1. In both these cases, 50% changes, and it becomes some wavelength lambda 2. Now, quantum mechanics does not allow me to do measurement in 45-degree, 135-degree, diagonal, anti-diagonal basis, and HP basis. But it does not stop me doing the measurement of wavelength. So if I do the measurement on wavelength without testing polarization, and then I can count, I can use, if it is lambda 1, I know it is H. If it is lambda 3, I know it's V. So photons have different degrees of freedom, and it is possible to think of attacks with the other degrees of freedom. And many sources have this kind of weakness, but how to stop this attack? So you just need to put a circulator here to stop this. But then there are simple attacks like beam splitters are not based on, beam splitters are wavelength sensitive. So when I am talking about 50-50 beam splitter, usually in the BB84 kind of implementation, so the light comes from beam splitter. If it goes here, and in one side I put a measurement device, which is a polarizing beam splitter, and the 2 detectors. So horizontal light passes and vertical light reflects. So if the vertical detector clicks, I know it is vertical. If the horizontal detector clicks, I know it's horizontal. In the other side, I apply a wavelet and then polarizing beam splitter. So that performs plus minus basis measurement. So now, but if I change the wavelength, so this is showing the ratio. Normally, the I port 1 by I port 1 plus I port 2. So which fraction is traveling?
Anirban, sorry to interrupt. Just wanted to remind you of the time. You just have a couple of...
I'll be done. So it is just showing that if you are here, then the entire thing is going from I port 1. So if the whole light goes to port 1, then the device is bound to do a measurement in say 0-1 basis. And when it is 0, so if I send in this wavelength, the device is apparently Bob is thinking that he is doing a random measurement, but changing the wavelength, Eve can control that whether the measurement will be in 0-1 basis on plus minus basis. And in that particular case, she can control also the outcome. Here is another one. This is a more common attack. So we are trying to establish a lab, and we spoke to so many people that whether the suppliers can give me what kind of detectors, and nobody can give you a detector. So detectors will have a same efficiency at certain point time t. Otherwise, the detector efficiency varies like this. So now there is a possible attack called time shift attack. If Alice delay one pulse or delay the pulses with some difference, if the pulse reaches here, then you see the detector, a particular detector has more efficiency compared to the other. So more likely that this one will be clicked. And if the second pulse is sent here, then probably more likely this one will be clicked. So he can control that which detector will be clicked. This is a nice attack. So this is the last quick attack which I want to show. There are of course other interesting attacks like hacking strategies like sending a light and blinding the detector, or sending a light and doing something called injection locking. So these are our recent interest to see that what are the possible hacking things comes from the weaknesses of the devices. So this one is a nice thing. So here is a laser. It goes from a beam splitter, and this makes me the reference beam. It goes through modulator and comes here in circulator. So circulator allows it, if it comes from 1, it goes to 2, but if it comes back, it goes to 3. It follows a anti-clockwise path. So you can have anti-clockwise or clockwise circulator. So this light goes into Alice's port. Incidentally, everything reflects. So it is reflected back and come back to this detection scheme. So in detection scheme, there is a reference beam and this return beam. And with respect to that, I can detect that what phase has been changed or what has been happened here. So I can try to get returned light. So this is called Trojan horse attack in analogy with the Greek epics. So you see, this is a real experiment. So this is a connector, this is a variable attenuator, this is a phase modulator. So if you know the structure, that which are the optics kept there, so then you know that which optics has done what. And in the return flight, suddenly this intensity hikes will be there, and from that we can try to disclose what is happening inside Alice's box. So what is the trick? So Alice should put another circulator to stop that no such light comes into Alice's port. So we end up with a cartoon which one of my PhD student has drawn. So this is Trojan horse attack summarized. So this boy, we wrote B for Bob, tells Alice that I don't trust you. So Alice asks why, and Bob says that because you reflect light. So Alice said that that's why you can see my beautiful face. If it is not reflecting, then you should not have been able to see me. And then Bob says that, well, but since you reflect, Eve can also see you. So then Alice come up with a solution, then gift me a circulator. So that will stop Eve from seeing the reflected light. So these are certain aspects which needs more attention for our complete cryptographic solutions or to get more excitement. So with this, I'll stop here. And so these are some funding agencies in our group, but it's an old picture. Some of them has left now.
Okay. So thank you very much, Anirban, for a very nice and informative talk, and also the very nice cartoons. The floor is open for questions, but in interest of time, we'll just take a couple of quick questions. So please raise your hand. Please raise your hand. So there's a question by Soumya Kanti Bose. Soumya Kanti, can you unmute yourself?
Yeah, thanks for the talk. I just want to know, in case of semi-quantum QKD, when we go for the security proof, so what actually ensures the security? Like in quantum case, there are certain aspects that tell you that those kind of conditions are satisfied, it is secured. But in case of semi-classical or semi-quantum, what is that guarantees security?
Actually, the same policies, the same things yields the security proof. So only thing is that the number of turns in which you get access to such situation reduces. So when if does not know that which one will be measured by Alice, I mean by Bob or the clone key user. So if efforts leads to the same kind of problems, but the detection rate is lower. Technically, the security proofs follows the same kind of things, but the set of cases in which you can go for security proof is lower.
Okay.
Okay, thank you. And I'm sorry, but we're kind of running into the next session. So if you have any questions, please type them in the chat box, and I'm sure Anirban will get to them and answer them, or you can also email him. So with this, I now close this session, and I thank all the three speakers for giving such very nice talks. The next session will start in a few minutes at 5:15.
Thank you.